So far, we've only been looking at one variable at a time. In this session, we're going to start looking at the relationships between variables. One of the important uses of statistics is to understand how things fit together in order to answer questions like, does drinking more milk promote stronger bones? Or, do students who attend job fairs get jobs with higher salaries? Suppose we have some exam scores for a few students. Some are high, like the red and orange dots, and some are low, like the blue and purple dots. Is this all just random variation in exam scores? Or could there be something that accounts for why some students got high scores and some got low scores? Well, suppose we can find out how much time each student spent studying. If we look at the combinations of time spent studying and exam score, we see an interesting pattern. Students who spent more time studying tend to have gotten higher exam scores. There's a relationship between these two variables. If we have statistical evidence of a relationship between two variables, then we can construct a statistical explanation of one variable using the other. The statistical explanation might answer the question, why does she have such a large salary, by saying, well, turns out she went to job fairs. In this sense, going to job fairs is used to explain graduate salaries on average. Now, these statistical explanations are always incomplete. There are lots of other things that go into why a graduate has a large salary, but they're useful in understanding relationships between things in the world. Sometimes these statistical explanations sound like causal explanations. She has a large salary because she went to job fairs, or job fairs caused her large salary. But a statistical explanation may or may not be causal. Despite the way we talk about statistical explanations, they're not necessarily causal, and there is an additional argument that you have to construct in order to make a causal claim. We're not going to worry about causal explanations here, and just focus on statistical ones. So in these statistical explanations, there are two kinds of variables. The response or dependent variable is the quantity to be explained or predicted, or on which comparisons will be made. The explanatory variable, also called an independent variable or a predictor, is a variable used to explain or predict the response variable. Here are some examples. Job fairs might be used as an explanatory variable for salary, the response variable. Drinking milk might be used to predict bone strength. Doing well in high school might be used in a statistical explanation for doing well in college. Binge drinking might be used to predict GPA. In a causal explanation, which variable is the explanatory variable and which is the response variable matters quite a bit. Does drinking milk cause strong bones, or does having strong bones cause people to drink milk? In a statistical explanation, on the other hand, either variable could serve as the explanatory variable or as the response variable. But even though you could use either variable in the pair to explain the other in a statistical explanation, we usually like to think about statistical explanations similarly to causal explanations. It makes more sense for us to think about how going to a job fair could explain a person's later salary instead of thinking about how we could use salaries to explain whether people went to job fairs. Now, the relationship between two variables that we use to construct the statistical explanation is called an association. This exists between two variables if a particular value for one variable is more likely to occur with certain values of the other variable. For example, in the association between studying and exam scores, higher exam scores were more likely to occur with larger amounts of study time. In age and height, it would be very unlikely for a 2-year-old to be 6 feet tall. If we think about happiness and air temperature, it could be that people are happier when the temperature is around 70 degrees and unhappy when it's around 100 or 30. Some questions we'll want to answer about association will be, is there an association between two variables? What kind of association is it? And how strong is the association? First, let's look at associations between discrete variables, that is, between variables that have either a nominal or an ordinal level of measurement. One useful tool in analyzing association between nominal and ordinal variables is a contingency table, This is a table that shows the number of observations, or the proportion of observations, for all of the combinations of possible values of two variables. This contingency table shows the employee type, either executive or production worker, and political affiliation, Democrat, Republican, or Independent, for a sample of 140 employees. In this sample, there were 5 Democrat executives, 34 Republican executives, and 48 executives in total. Now suppose we want to know if being an executive or production worker makes a difference for the distribution of political affiliations. Since there are more production workers than executives, we can't just look at the numbers in the table directly. We have to take into account the difference in group sizes. To do this, we rely on a conditional proportion. This is a proportion of observations with a particular value for one variable, only considering those observations that have a certain value for the other variable. Usually we find conditional proportions of the response variable given a value of the explanatory variable. In this example, let's find the proportion of executives who are Republicans. That is, the proportion of employees who are Republicans, given that they are executives. Or another way of putting it, considering only the executives, what proportion are Republicans? Usually when finding a proportion, we divide the number in our chosen group, Republicans, by the total group size, all employees. For a conditional proportion, instead of using the whole group, we only consider observations with the given value, executives. So to find the proportion of executives who are Republicans, we take the number of employees who are both executives and Republicans, 34, and divide it by the number of employees who are executives, 48. This gives us 71%. 71% is the conditional proportion of Republicans given that an employee is an executive. Now we have a contingency table. How do we tell if there's an association? An association exists if the conditional distributions are different for different levels of the explanatory variable. That is to say, if the value of the explanatory variable makes a difference in the distribution of the response variable. For example, if we take the employee type as an explanatory variable for political affiliation, we ask whether being an executive or being a production worker makes a difference in terms of political affiliation. It turns out that 71% of executives are Republicans in this sample, whereas only 23% of production workers are Republicans. So there is an association between employee type and political affiliation, because the proportions of employees with each political affiliation are different for each type of employee. If there is no association between two variables, we say that the variables are independent. Two variables are independent if the conditional proportions for one variable are the same, irrespective of the value of the other variable. Suppose our contingency table for employee type and political affiliation looked like this. Then employee type and political affiliation would be independent, because the proportion of Democrats would be 68% for both executives and production workers. That is, it doesn't make a difference for political affiliation whether an employee is an executive or a production worker. There is no association. For continuous data, we usually can't construct a contingency table since there are very few observations that take on any one particular value. Every observation is slightly different. Instead, we can use a scatter plot to investigate the association between two interval ratio variables. We can talk about two types of association. A positive association occurs when two variables tend to increase or decrease together. That is, when one variable is high, the other tends to be high as well, or when one variable is low, the other tends to be low as well. A negative association is the opposite. When one variable is high, the other tends to be low, or when one variable is low, the other tends to be high. For example, in this scatter plot of the number of repetitions that University of Georgia women athletes can do at 70 pounds and 55 pounds, we see that when an athlete can do 40 repetitions at 55 pounds, the athlete can do somewhere between 20 to 30 or 35 repetitions at 70 pounds. Whereas if an athlete can only do 10 repetitions at 55 pounds, then the athlete can only do between, say, 0 and 10 repetitions at 70 pounds. The more repetitions that the athlete can do at 55 pounds, the more repetitions she can do at 70 pounds. In this example, we see a scatter plot of the body fat and number of sit-ups that high school female athletes can do. As body fat increases, the number of sit-ups decreases. If body fat is at 20, then an athlete can do somewhere between 25 and 40 sit-ups. But when body fat increases to 35, the athlete can only do between, say, 10 and 20 sit-ups. This scatter plot shows height and body fat of University of Georgia women athletes. We don't see much of a relationship between the two. For athletes who have heights of, say, 62 inches, we see that body fat ranges between, say, 10% and 20-some-odd%. If height increases to 70 inches, we see that body fat still ranges between about 10% and 20-some-odd%. There is no relationship between height and body fat in this sample. Some associations are linear associations. These are associations that can be described by a straight line. If we take a look at the scatter plot of the number of repetitions that athletes can do at 55 and 70 pounds, we see that the dots in the scatter plot tend to follow this straight line. If we look at this plot, on the other hand, we see the frequency of wing beats of swallows versus the airspeed of the swallow. Notice how when the airspeed is low, say 4 meters per second, the wing beat frequency is high, between 8 and 9. Then the wing beat frequency decreases as airspeed increases until about 8 to 10 meters per second. Then, as the airspeed continues to increase, the wing beat frequency goes back up again. There's a clear association between airspeed and wing beat frequency. At certain airspeeds, the wings are likely to beat more frequently or less frequently. But this isn't a straight line association, because the wing beat frequency decreases and then increases again as airspeed continues to increase. This kind of association is called curvilinear, which is just the silly name that statisticians came up with. In addition to telling the direction of the association, we can also get a general sense of the strength of the association by looking at the scatter plot. Strong associations will tend to have points that are more closely packed together than weak associations. For example, if we look at the scatter plots for the number of repetitions at 55 and 70 pounds and the scatter plot for height and total body weight, we see a positive association for both of these. But on the scatter plot on the left, we see that the points are more closely packed together, whereas at the scatter plot on the right, the points are a little bit more spread out. The association on the left is stronger than the association on the right. Instead of eyeballing it, we can measure the strength of an association with the correlation. This is a numerical summary of the strength of a linear association. To calculate a correlation, you have to have interval or ratio data. The correlation varies between -1 and +1. Values of +1 indicate a very strong positive association, and values of -1 indicate a very strong negative association. Values of 0 indicate no association. One thing to note about correlations is they don't depend on the scale that you use. If you calculate height in inches and then change to height in centimeters, you're going to still get the same correlation with body weight, no matter whether you're using pounds or kilograms. In the plots for University of Georgia women athlete, we see that the correlation between the number of repetitions that the athletes can do at 55 and 70 pounds is 0.94. This is a very strong positive association. And the correlation for height and total body weight is 0.74. This is still a fairly strong association, but not quite as strong as the one on the left. If we compute the correlation between height and body fat for University of Georgia women athlete, we see that the correlation is 0.1. That's close to 0. That indicates that there is not a strong association between height and body fat. Look what happens when we try and compute the correlation between airspeed and wing beat frequency for the swallows. We get a value of -0.12. -0.12 is fairly close to 0, which would suggest that there's not a very strong correlation between airspeed and wing beat frequency. That might be surprising since we seem to notice a very strong association between airspeed and wing beat frequency. The reason why the correlation is so close to 0 is because correlation is a measure of the strength of a linear association. And as we said before, the relationship between airspeed and wing beat frequency for swallows is curvilinear. If we were to draw a straight line that tried to fit these points, it might look something like this. It would be pretty flat and maybe have a slightly negative slope. The point here is that the correlation does not always show whether there's an association. It only shows whether there's a linear association or a straight line association. Because curvilinear relationships could exist, lack of correlation does not mean lack of association. So always plot the data to see if you might have a curvilinear relationship.